All right, let's have a look at head loss. It starts on page 107, and that is chapter 11. All right, when water starts to flow, it rubs against the walls of the pipe, and you also get turbulence. And this friction on the walls of the pipe and the turbulence causes head loss. Head loss is energy loss. Basically, when you get this friction and turbulence on the walls of a pipe and also in fittings, you get a little bit of heat that then dissipates off into the atmosphere, and you lose that energy. There's two main categories of head loss. Major head loss occurs when the water flows in a pipe. Minor head loss occurs when the water flows through a fitting. All right, now the basics of head loss is it increases with pipe roughness, pipe length, and fluid velocity. Those are the things that makes head loss increase. Fluid velocity can be created by a high flow rate and or a low pipe size. Head loss does not depend on pressure. Head loss is calculated using equations and charts. These methods were created around 1900, so more than 100 years ago. There's two common methods. The Hazen-Williams is the easier of the method, but it's the less accurate of the methods. We'll primarily focus on that, so that's the one we're primarily going to do. We're also going to look, though, at the more theoretically accurate, but more difficult to calculate Darcy-Weisbach method, too. So we'll spend most of our time on Hazen-Williams. We'll just do a little bit with Darcy-Weisbach. So let's have a look at Darcy-Weisbach. Okay, and that is actually starts on page 118 of your book. Okay, so that's on 118. Now the formula for Darcy-Weisbach tells us that the head loss is a friction factor that describes the roughness of the pipe, multiplied by the length of the pipe, divided by the diameter, and then multiplied by the velocity head, which is v squared over 2g. So to get the head loss, you find a friction factor, multiply it by the length, because the longer the pipe, the more the head loss, multiply it by the velocity head, which again, as the velocity head goes up, that means the velocity is higher and you have more head loss. And then you also, though, divide it by the pipe diameter, because a bigger diameter leads to a lower velocity, and that actually decreases head loss. So it's F L over D times V squared over 2G. Now, all the lengths in this formula are measured in feet. And keep in mind that G is 32.2 feet per second squared. Now, one of the things you have to do to calculate this is find F, the friction factor. There's two types of flows. There's laminar flow and turbulent flow. The vast majority of flow in the water systems we'll be dealing with is turbulent. But we do have to check this, okay? And the way we check it is with something called the Reynolds number. Reynolds number is the diameter of the pipe times the velocity times the density over the viscosity, okay? Now there's a table on page 58 that we can use to find these values. Okay, so that's on page 58. That's where you go to find the density and the viscosity so you can calculate the Reynolds number. Now when the Reynolds number is bigger than 2100, the flow starts to become turbulent. Okay, so one step in finding this F factor is to find the Reynolds number. The other is to determine the relative roughness. To do that, you kind of have to know what's going on inside the pipe. A pipe isn't perfectly smooth. There's little pits and little bumps and things like that. Okay, so we have this letter. This is a Greek letter, epsilon, that's used to describe the largest imperfection in feet in the pipe. And there is a little chart on page 120 that shows typical values for different types of pipe. You then divide that by the diameter of the pipe. Both of those values are taken in feet. When you do that, when you take epsilon, the largest imperfection, divided by d, the pipe diameter, you get something called the relative roughness. Okay, when you have the relative roughness and the Reynolds number, you can then determine the friction factor by using this table here. Okay, this is called the Moody diagram, and it's on page 120. It has that little chart with these epsilon values embedded in it right there. This might be best shown with an example. Okay, the example is on page 121. It's kind of laid out to work through. Now, I want to go through one example on this stuff. After this, we're going to go right to the Hazen-Williams approach because it's a more straightforward approach, but I do want to cover one example here. So let's find the head loss for 600 gallons per minute flowing through 800 feet of 6-inch unlined cast iron pipe. The temperature is 70 degrees. So first thing we want to do here is find the Reynolds number. To do that, you go to page 58 and look at the chart there. We have 70 degrees. Now, I think there is a typo in your book. It says 60 degrees. Let's use 70 instead, okay? So on page 121 at the top, it says the temperature is 60 degrees. Let's change it to 70, okay? All right, now if we got 70 degrees, we go to that chart on page 58, we can find the viscosity, it's 0.0000203, and we can find the density, it's 1.936. Okay, so we get the viscosity and the density, and we write those down. When we have those, if we know the pipe diameter in feet, it's 6-inch pipe, so that would be a 1/2-inch diameter pipe. And if we know the velocity, now we can calculate the velocity. You know, we have the formula Q equals VA. We can find the velocity by taking Q, the flow rate, and dividing it by the area. However, there's another way to do it. And there's the Hazen-Williams chart, which is on page 108, has the velocity given for different pipe sizes and flow rates. So rather than going through that calculation of Q over A every time, you can just look at the chart on page 108 from now on, okay? So you have the flow rate, and then you have the pipe size, you can find the velocity. So what we have in our example is we've got 6-inch pipe with a flow rate of 600 gallons per minute. So using that, we can find the velocity. We just head on over to this chart on page 108. We looked at 6-inch pipe, 600 gallons per minute. And we get the velocity right there on the right-hand side, 6.81. Okay, so there's the velocity, a lot easier than running through all the calculations there. Okay, so what we've got now is we've got the pipe diameter in feet, we got the velocity, we've got the density, we've got the viscosity. We plug all that in, and that gets us the Reynolds number, which is a dimensionless number. In this case, it's 325,000, which in scientific notation would be 3.25 times 10 to the 5. Okay, so there's the Reynolds number. Now, the next thing we want is the relative roughness. We're going to look at this little chart that is on our Moody diagram, okay, right there. And we're going to see for what we have, which is unlined cast iron pipe, okay, the epsilon value in feet is 0.0008. I'm on page 120 for the Moody diagram. Okay. All right, so that's right there. I'm going to take that number and I'm going to divide it by the pipe diameter, which is 6 inches, half a foot. So this is all in feet, so 0.0008 divided by 0.5 gets me what's called the relative roughness, 0.0016. Okay, so now I've got the Reynolds number, I've got the relative roughness, so I can go to that Moody diagram on page 120. I can then locate these things. All right, so I'm after 3.25 times 10 to the 5th for the Reynolds number on the bottom of the chart. There's 10 to the 5th, go a little further over to 3, and a little bit beyond that is 3.25 times 10 to the 5th. So I draw a vertical line there. Then over here with these lines that curve up, I'm going to find the relative roughness. I'm looking for 0.0016, here's 0.0010, 0.0020. I'm kind of roughly halfway, or probably a little bit above halfway on that, and I just follow those lines in. So I've got a line as best I could draw it in here, and I keep going with that, following those curved lines until I intersect my vertical line. Once I've got that, I can read it to either the right or the left-hand side of the graph. I went to the left. It looks to be roughly 0.023. So there's my friction factor F. Okay, now once I've got that, I take 0.023, my friction factor, multiply it by the length of the pipe, 1,800 feet. Take that times the velocity squared. Okay, so that's 6.81 feet per second, and that's quantity squared there. Divide it by the pipe diameter, 0.5, divide it by 2, and divide it by gravity, 32.2. That works out to be a head loss of 59.63 feet. So that's one way to get head loss. Now, that's probably the most accurate method we've got. It does depend on knowing the condition of your pipe and being able to make a good estimate of epsilon, but it's theoretically accurate if you know that. Now, getting that actual number, of course, can be very difficult. It's usually estimated by the condition of your pipe, but that's the best shot we can get at calculating head loss. Now, there's another method, okay, that's a lot easier. I just wanted to go through one of those examples, but normally how we're going to do this if we do it by hand is we're going to use the Hazen-Williams chart for this. The Darcy-Weisbach method is probably embedded in a lot of software because it's quite accurate, or it's as accurate as we can get, I should say. The Hazen-Williams I would use if I'm going to do it by hand. All right, so if I'm going to do it by hand, I'm going to go to this Hazen-Williams chart on page 108. Okay, and I'm just going to look up 600 gallons per minute and find the head loss for 6-inch pipe. So 6-inch pipe, 600 gallons per minute, I get 4.65 feet per 100 feet of head loss. And that's what that is. Then I know I have 1,800 feet. So if I have 4.65 feet per 100 feet of head loss, and I've got 1,800 feet, I take 4.65 and I multiply it by 18. This is the head loss per 100 feet. I've got 18 100-foot lengths. I get 83.7 feet. So that's another way to work this out, okay? It's with the chart. The chart is based on what are called different C factors. I've got a C of 100, which is the approximate C when you have unlined cast iron. You can use that, and based on that chart, then I can calculate the head loss. So I just look up the head loss for my flow condition and pipe size and multiply it by the number of 100-foot lengths of pipe. Now you might notice these numbers are a bit different. And that is something to realize, is that head loss is not a perfectly accurate number. It's based on a lot of assumptions. So I don't calculate head loss with the expectation I'm getting an exact number. It's a ballpark number, and I treat it as such. But that's how we go about calculating it. Okay. So going back to the Hazen-Williams method on page 107 and 108, there's the formula for it. A little bit involved, as you can see, more involved than the Darcy-Weisbach. It looks to me like these two scientists went into a lab and just ran a lot of tests and tried to make a best fit curve to what they had. That's kind of what it looks like to me. They've got the head loss is equal to 147.85 times Q, the flow rate in gallons per minute, divided by the roughness coefficient, C, divided by D to the 2.63. Now, D is the pipe diameter in inches to the 2.63 power. And then you take this and you take it all up to the 1.85 power. Kind of a little bit of a difficult formula to plug everything into and run. So there's a chart built for it that we use. Okay, so the formula is commonly shown on a chart. The chart uses C100, which is the C value for unlined cast iron, which was kind of the standard pipe when they did all this research. So that's kind of their reference number. The chart gives head loss in feet per 100 feet, so keep that in mind. It also has a column for velocity as well as head loss. So we use these charts quite a bit to find head loss when we're doing it by hand. Okay, so we'll pick up on Wednesday with this. Okay, the homework that was due this coming Wednesday, the 6th, is now due the 13th. Okay, so we're going to push that back a little bit. So the homework that was due the 6th is now due the 13th.